Hello and welcome to the AI Research Roundup. I am Alex, your host. Today is May 9th, 2025. We are looking at a research paper from Hugging Face's trending list, published just 5 days ago, titled Attention Mechanisms Perspective, Exploring LLM Processing of Graph Structured Data. This paper investigates how large language models, or LLMs, process graph structured data. This type of data is all about connections between items. LLMs use attention mechanisms, essentially how they decide what to focus on. The authors explore why LLMs sometimes struggle with graphs compared to specialized graph neural networks, or GNNs. Alright, so to understand how LLMs handle this graph data, the authors first looked at attention distribution. This figure shows exactly that, with 3 plots for different datasets. Each plots the density distribution of attention scores. Tokens are basic data units, words for text, or items in the graph called nodes. The quote, attention score measures how much the large language model focuses on each token. See how the dashed lines for trained node tokens shift from the solid lines? This change indicates that after training, the large language model learns to pay different attention to the graph's nodes. Building on that understanding of attention, this table then details, quote, connectivity information disruption performance. So, the researchers deliberately altered the connections, the graph's topological information, to see how it affected the large language model's accuracy on node classification. This task is about correctly categorizing each node based on its connections and features. Across several datasets and different levels of this disruption, from raw or original data to more severe changes, we see the accuracy. Often, performance remains quite stable until high disruption, suggesting the large language model is not fully using that crucial structural information. Okay, so to dig deeper into how large language models actually look at these graph structures, these next plots illustrate the attention scores, essentially how much focus the model gives to different nodes. The upper row shows node-to-node attention, while the lower shows text-to-node attention. A hop, by the way, just tells us how many steps away one node is from another in the graph. Notice how the node-to-node attention often concentrates on later nodes or shows unusual spikes. This suggests issues like an attention sink, where focus gets stuck, or a skewed line sink, a lopsided attention pattern that hinders the model from properly understanding the graph's connections. So, given those attention patterns, the researchers then looked at model performance with different attention window configurations. This table shows the accuracy for different values of K, which stands for Global Linkage Horizon. Think of the Global Linkage Horizon as how wide a view the large language model gets of the graph's connections, from K equals 1, a very narrow view, up to K equals 4, a fully connected view. We also see UniD for unidirectional and BD for bidirectional attention, referring to how information flows. Interestingly, the best scores are often with intermediate K values, not always the widest view. Alright, so to visualize these attention issues more concretely, this figure shows an, quote, attention score interaction matrix on the left. This matrix is essentially a map, charting out how much attention is paid between all the different nodes in the graph. Then, on the right, we see more detailed, quote, attention maps. These zoom in on first-order nodes, those directly connected to a central node, and second-order nodes, which are 2 steps away. These visuals clearly highlight the attention sink and skewed line sink problems we touched on, where attention gets misdirected, hindering the large language model from truly understanding node-to-node connections. Building on those visual insights into attention problems, this table shows the transfer performance of models across different K values. The rows indicate the Global Linkage Horizon, or K, that is, the view of connections, used during training with unidirectional or bidirectional options, while columns show the K for testing. What is really interesting is that training with an intermediate K, perhaps 2 or 3, then testing with a wider view, like K equals 4, often yields better results than always using the widest view. This points to a practical way to enhance model performance. So this idea of adjusting the global linkage horizon during training and testing offers a really practical path forward. In essence, this research shows that while large language models can indeed perceive graph data and understand text-to-node links, they struggle with the crucial node-to-node relationships. This is largely due to issues like the attention sink we discussed. But training with a more focused, topology-aware view, that is, a view that understands some of the graph's connection structure, and then expanding that view for testing, seems to be a promising solution. That is all for this AI Research Roundup. Thanks for tuning in.